Hello. Today I'd like to introduce you to a very special video. It's a walk back in time to the early days of North American aviation and its Autonetics Division. The video will illustrate how the vision of the company's pioneers evolved into the realities of today. This is the first of a series of videos that will preserve the heritage of Rockwell's Autonetics organization for future generations. Our goal in producing this particular video was to capture the historical events and technology advancements that led to the ICBM guidance and control systems of today. And as we experience the end of an era, it's crucial that we recognize Autonetics' role in a very important segment of Cold War era activities. Each of the people featured in this video made significant contributions in shaping the future of Autonetics. One in particular was a key player in our heritage, John Moore, the first general manager of Autonetics. He and the others will give you a first-hand look at what it took to get us where we are today. So sit back, relax, and enjoy the show. I know I'm going to.
I'm most proud of the people that I was instrumental in hiring, the people that I selected, the kind of people from which have come 11 CEOs and 8 COOs of major corporations outside of what is now Rockwell.
Now, I think the thing I'm most proud of is the amount of teamwork that we managed to put together within our own organization, the amount of talent that we were able to put on this program, and the relations that we had with our customer and the customer's other associate contractors. It was a very tightly knit program, and without that same kind of closeness throughout the program, it would have been absolutely impossible to meet the goals and requirements that we did.
It's hard to pick any one particular item, but I know when we flew the first Minuteman III, I think that was an accomplishment. When we started the Minuteman III into the silo, when not only did we get them into the silos, but we beat every reliability incentive, every price incentive, and I can recall them delivering this huge check. They put it on they made a model of a big check that was presented to the corporation as our share of these incentives, and these were very proud moments that we had.
I guess I would have to say it was the first flight of Minuteman III, which was just about a 100% success. Prior to the time we had any flight failures, that first flight went like clockwork and deployed the objects in order, and we were sitting in the ops center in building 235 with a phone hookup to the Cape. To see it happen, and happen just the way it was supposed to happen, I thought was kind of the peak achievement of my career.
My personal idea of what was the greatest achievement, I thought was probably the Minuteman III silo reliability. Well, to make a long story short, not only did we achieve that, but we achieved, much greater than anybody ever imagined would be possible, and so I felt very good about that.
In a larger program sense, I think the success that led to the first flight on Peacekeeper in managing an organization, a very capable organization, but sorting out all the problems, paying the right either personal attention to them or having other teams pay attention to them, and ultimately then a program that led to a major underrun.
A lot of people have asked me what I'm most proud of on Peacekeeper, and I've thought a lot about it. And I think the thing that I'm most proud of are the performance of the people. Absolutely fantastic. So that's what I'm really proud of, is the ability to make the team work, to facilitate what had to be done without having to coerce anybody. When you get to heaven, if there's a peacekeeper program, I'm going to be first in line for that job, brother. It was a real run.
Autonetics' background can best be described as a history of achievement. That history was made possible by a group of very talented individuals. In addition to the pioneers who you have just seen, we can't forget the contributions of leaders we weren't able to interview, such as Norm Parker, Fred Eyestone, George Lease, Don Williams, Joe Geisler, Bob Caseby, Ernie Manuel, and Ernie Youngren. Hello, I'm Don Southwell, a longtime employee of Rockwell International's Defense Electronics Organization. I see you've already met some of my former bosses and colleagues and are probably wondering why they're feeling so proud. It was their vision, their ingenuity, and that of their predecessors that led to the accomplishments of the men and women at North American Aviation and its descendant organizations, such as the Autonetics Division. In order to fully appreciate the depth of their emotion, let me set the stage by stepping back in time to that period when our nation was threatened with the fear and destruction of war, to the mindset of the people, some of them your friends and relatives, who lived through the terror of an actual war. To many of us, World War II was an event we read about in history books. Among other things, it was war during which German technology and guided missiles became legendary. Two Vengeance weapons, the V-1 and V-2 rockets, were the most dreaded. The V-1 was a subsonic pulse jet, essentially a pilotless jet airplane, and the V-2 was a supersonic, intermediate-range ballistic missile. World War II was also the event from which North American Aviation, or NAA, emerged with a new place in American history. In addition to producing a total of 42,683 aircraft, more than any other American plane maker, the company produced the most successful trainer, fighter, and medium bomber in American history. Under the visionary leadership of two North American aviation pioneers, James H. Dutch Kindleberger and Leland Lee Atwood, a small group of scientists and engineers specializing in electromechanics was formed into the Aerophysics Laboratory. In those early days, inertial navigation was a new science and art. Up to that time, pilots navigated through the use of dead reckoning, a method of advancing from a known position to a later position by adding one or more vectors that represent known courses and distances. It had become clear that none of the existing techniques was satisfactory for the military navigation problem. The Aerophysics Laboratory was moving rapidly toward making inertial navigation a standard technique.
As our advanced research projects extend our scientific frontiers,
in 1948, John Moore was right in the middle of these historic changes as one of America's leading authorities in the emerging field of automatic navigation and inertial guidance.
For the company and employee alike.
The genesis of the inertial navigation activity at then North American Aviation, now Rockwell, was sometime right after the end of World War II. It was the foresight of Dutch Kindleberger and Lee Atwood in establishing the Aerophysics Laboratory under Dr. William Bollet, with as his associate Dr. Nils Edlefsen, which then in what was known as the beginning of the missile era got the Air Force's Navajo Missile Study Program, which later became a full-fledged missile program. It was determined that this would have to have inertial navigation, and because inertial navigation was originally part of the German activity, people before I came with North American Aviation had thoroughly researched the activities of the Germans, particularly the Germans which had been brought over with Professor von Braun and originally at Fort Bliss and then taken to the Redstone Arsenal. key in those days was John Slater. He was what I would call the spiritual leader of the spiritual inspiration of the inertial navigation activity at North American. Another very important leader was Fred Eystone. Fred was totally different from John Slater in that he was much more of a manager and less of a visionary. But they both were there when I got into North American on the 2nd of February 1948. The Navajo program was the major program for which inertial navigation was going to be an essential part. And the Navajo, as originally conceived, was a rocket-boosted, ramjet, more than Mach 3 cruise missile, cruising at somewhere between 70 and 80,000 feet. The idea being that it could get to targets in the Soviet Union in about 3 hours. The Navajo guidance as initially conceived was unclear because it wasn't at all certain that we could do a good enough job with inertial instruments to make it possible to use an all-inertial navigator on the Navajo. So although we began with the development of the XN-1, which was the first inertial navigator ever to fly, and which flew out of Downey in a C-47 in 1950. We also had going on at the time daylight star tracking work for something called the XN-2. In the meantime, our inventors, and I don't remember who it was, but I'm sure that John Slater had a lot to do with it, came up with a concept of 6 gyroscopes, 3 of which would be reversing while the other 3 continued to stabilize the inertial platform. This was called the Navan principle, and we did it that way because it was spelt the same way forwards and backwards. And Navan had to be an acronym, so it was called Navan, North American Vehicle Auto Navigator. But we really did it that way because of the fact that we had a reversing gyro system, and we wanted something spelled the same way forwards and backwards. This 6 gyro system achieved enough accuracy to be considered by itself for the Navajo guidance, and effectively brought an end to our work on daylight star tracking. In July of 1957, the Navajo was canceled. Autonetics had been formed in November of 1955 with 7,800 people. We went through a very painful cutback so that at the beginning of 1958 we had 5,400 people. In any event, from the cancellation of the Navajo, we had a series of successes. We won, North American won the Hound Dog missile. We had the guidance and control for it. We got the reins, which was for what was then the A3J and later became the RA-5C, made by the Columbus Division. Reins meant radar-equipped inertial navigation system. It was a nav bomb system. Now, you may be interested in how the Autonetics Division got its name. We wanted to have a name which began with A, so it would be at the top of lists. And so we said, well, probably everything we're going to do is going to have auto in it, begins with A, and somebody in the advertising area that North American used had learned about cybernetics, and they thought that netics would be good, and we said, well, everything we have probably end in X. And so we came up with Autonetics. And the only mistake that we made in picking Autonetics was its length, because it was too long to have large letters. And in a subsequent chance I had to pick it, instead of having 10 letters, I ended up having 6, so that the letters could be larger. But that's how Autonetics got its name.
In 1958, Autonetics played a crucial role in making history. The historic cruise of the world's first atomic-powered submarine, the USS Nautilus, under the treacherous ice cap of the Arctic Ocean to the North Pole was made possible by the Autonetics N6A1, a modified version of the Navajo inertial navigator.
The interesting thing about the NAVAN system was that when we packaged it for the Navajo, we also anticipated the fact that it would be useful in submarines. And that was back in well, I've forgotten what time exactly, but 1952 or 1953. So we purposely made the size of that platform 1/4 of an inch smaller than the submarine hatch. That later became an important reason why the Navajo inertial navigator was the navigator which, along with the engineer from what was then actually Autonetics, Tom Curtis, caused the Nautilus and the Skate submarines to be able to navigate under the ice over the North Pole. It was done with the anticipation, back in the early 50s, that we would be able to use that scheme for a submarine autonavigator. Now, of course, we use submarine autonavigators that are totally different because we can make so much better instruments. But in those days, it was interesting, I thought, that we had that much foresight.
In 1959, Autonetics began delivering inertial navigation systems for Polaris missile-carrying submarines, the N7A Ship's Inertial Navigation System, or SINS. Today, virtually all the U.S. Navy submarines are guided by Autonetics-built navigators. All of these achievements established Autonetics as a major producer of inertial navigators for missiles and nuclear-powered submarines. We had entered the big leagues. And soon thereafter, Autonetics would assume a critical role in the ICBM guidance and control technology. With the Soviet launch of Sputnik in 1957, the corridor of space had suddenly opened. Our nation stood vulnerable to nuclear weapons which could be boosted through space to devastate this continent. They would reach our heartland in a matter of minutes after launch. America needed a credible deterrent, one that could react almost instantly to close the so-called missile gap. It was clear at the time that the pioneering work with the Thor, Atlas, and Titan liquid propellant ballistic missiles had proceeded to the point of recognizing that such systems, largely due to high cost and slow response time, could never be the backbone of the strategic missile force, which was to be a cornerstone of our strategic military posture. The military quickly responded, and Minuteman was conceived. In idea only, its reality lay far beyond the state of the art.
In 1957, there was a competition, and the competition was for a 3-stage solid rocket engine missile called the Minuteman. We won that competition, and as I recall, we learned about that on the 20th of July, 1958. We saw the threat to the Navajo program of the ballistic missiles.
Well, the Minuteman I program was a major undertaking, as you know, in terms of doing things different than had been done before. And when we won the proposal, we discovered afterward that our proposal really didn't win, per se. What they found very attractive in it was a free rotor gyro, because that meant the That opened the way for very long life on the gyros. And they liked our organization, where we had everything under one roof that could accomplish this integrated guidance and control system that they wanted. And this is the first time that anything this broad had ever been done.
To make the Minuteman missile a reality, the Air Force and industry embarked on a technical adventure that would focus talent, ingenuity, and scientific daring on the nation's first quick-reaction, solid-propellant intercontinental ballistic missile. And Autonetics was at the forefront of this development. The initial contract was for research and development of a completely integrated guidance and control system. It was the start of what was to be the foundation for the Autonetics ICBM development and production work that has carried the nation's defense into the 1990s. Since the Minuteman weapon system depended upon deployment of continuously operating missiles in widely dispersed, unmanned, and underground silos, it was necessary that the guidance and control system meet unprecedented requirements for reliability and in-commission rate. To understand the extreme degree of reliability to be obtained, just think of your television set at home. If the components in your TV had the same reliability as the components in Minuteman, it could be expected to run continuously for 25,000 years. Every wire, component, and connection must be perfect. Not just good, but perfect. Furthermore, the Minuteman system was required to inertially guide and control the missile with an accuracy 4 times better than that achieved in comparable prior guidance systems. It was to perform as a completely automated system in its day-in, day-out operation and readiness testing in an isolated, attack-resistant underground silo.
One of the big tasks that we undertook was to give the computer a greater and greater role in controlling that guidance and control system. And it was no secret that the major thing that we were trying to do different than had been done before was to minimize the massiveness of the ground equipment and of the launch facility. So here was this launch facility designed to be placed out in the middle of nowhere as far as 150 miles from the support base. It was unmanned, and it was perhaps 10 to 30 miles away from the launch control center that could control that silo. And so inside, everything had to be totally automated. And we tried to put as much of that into the airborne system as we could in order to eliminate a lot of ground equipment. We were fairly successful in doing that. We kept the system just as simple as we possibly could. It was a system that was viewed as the key element of what was then a massive retaliation scenario, where the system was to be ready to go at a moment's notice and could be dispatched in total, if appropriate, as a retaliatory kind of strike. And that meant that we could predetermine the targets, and we could enter those targets into the computer. We could align the missile itself in the direction that it was going to fly, and then we simply kept its alternate targets along or close to that same direction. We went to the use of electrohydraulic actuators for the nozzles on all 3 stages. And that brought up some new requirements in the basic electrical business that needed to be met. One is that we had to develop a primary activated battery, one that could sit for years and years and years in a dormant state and then be activated instantly and have the electrical and energy characteristics that we needed for the subsequent flight. And that was a major development of this program. Something as mundane as a battery consumed a great deal of technical effort. Another area that was simply not to be found were electrical connectors of the characteristics that we needed in terms of reliability, size, weight, things like this. And so there was a major program launched to develop electrical connectors. And that program probably advanced the state of connector art throughout the U.S. by a significant amount during the course of the program. It was successful. The battery program turned out to be very successful. The system met its size and weight restrictions, which was very important because we had a very small missile, and at an early stage in the program made the decision not to upsize the missile, but to keep the missile small, and that meant in order to achieve the range that we had to get, we simply had to keep the weight down. So there was that reevaluation and a decision made to stay on course and go with as light a weight system as we could and still get the range that was needed for Minuteman.
I came to work for Ernie Youngren in the Minuteman Division in 1960. Tom McNary came about the same time. McNary was the R&D program manager, and I was the production program manager. We had a program that just doesn't happen today. We had a concurrent program. The initial contract was issued in 1958, and the production contract required that the first 10 missiles be installed at Malmstrom Air Force Base, I believe was October of 1962. Today, this would be unheard of. When you're starting to produce in numbers like that, lots of things happen, especially on a concurrent program. Devices that should be available aren't available. Devices that should have passed their aging processing didn't pass. What do? You have production that has to go ahead. And I think we were the first ones who had a real configuration control system over the life of the whole program. It started with Minuteman. Did not exist prior to Minuteman. They used to fly Atlases, and they had an idea of what was in it, but they couldn't tell you exactly what was in it. Minuteman, we could tell what was in it. We knew exactly where all the hardware was.
Not only were all guidance and control system requirements met, most of them were exceeded in ways that increased system cost effectiveness, and every weapon system deployment schedule was met. Through historic film footage, let's relive the excitement at Autonetics when the first Minuteman was test launched.
Early in 1961, such an event occurred on a launching pad at Cape Canaveral. A Minuteman missile was being prepared for the first test firing. As the months of work and millions of man-hours of effort embodied in the missile approached the crucial moment of test, tension, anxiety, and hope mounted. Fond dreams and high expectations would soon be fulfilled or destroyed. While flight test personnel continued the launch preparations in the blockhouse, a telephone connection with the Cape relayed latest information to the Autonetics plant in Downey. As the countdown progressed, the growing tension was mirrored on the faces of all. And here it comes.
Climbing just beautifully. Did you hear the engine?
This was truly a shot heard around the world. A few days later, the people who built Minuteman participated in the excitement of the first flight through a closed-circuit TV rerun of the event. Minuteman's first flight was not only a successful liftoff, but each stage fired as planned, and the Autonetics guidance and control system successfully guided the Minuteman re-entry vehicle downrange to its target. At the time it entered the operational inventory, the Minuteman I had recorded the shortest development time from design to operation of any ballistic missile weapon system. No other weapon development had been as successful or as cost-effective.
We were able to produce a system that could align itself, calibrate itself, take care of itself, self-check, do all of this in a totally unmanned environment and stay there operating for literally years without substantial maintenance problems, because the slightest glitch in the system meant that the silo had to be opened, the parts of the missile had to be removed and sent back to a depot hundreds of miles away. It was a major undertaking.
Among the people that I found when I came to work here were what I considered very professional types, very professional, both in data systems, in navigation systems, and in the flight control area, both in the program management and the engineering. I like to think of myself as being the catalyst who brought them all together so that we were able to produce at these large quantities.
Minuteman I program was a very big undertaking, and fortunately we were able to assemble an awful lot of talent in an awful lot of areas, and that included the talent that the Air Force put in on the program and the tremendous talent that TRW offered as the overall technical director on the program. And I should also note that the Boeing company put some very, very good people on the program for their part of it.
In addition, we had some other very professional people in the Minuteman Division, people like Maurice Stone, Elliot Buxton, Chet Ballard, and a few others, and these were all people who were truly professional and did an outstanding job in helping us get there.
It was a program that we all loved, and we worked hard. We had a lot of pride in what we did, and it resulted in a lot of good teamwork and a lot of careful innovations into achieving the kind of goals that we were trying to achieve.
Both the Polaris program and the Minuteman program were programs unparalleled except possibly for Apollo and the Manhattan Project in the history of the world.
800 missiles in large quantities. I think we hit as many as 60 a month at one time, and that was unheard of, and probably still unheard of for the complexity of the equipment that we turned out. But it was done.
And so we were a part of all that history. And it goes back to the excellent people that we had managed to attract under the leadership of Dutch Kennelberger and Lee Atwood into what was, after November 1955, the Autonetics Division.
1,168 Minuteman I guidance and control systems were produced, and even before the first Minuteman I missiles were deployed in the field, development of the Minuteman II system began in mid-1962 to meet new and emerging requirements of our military posture. With the germ of an idea, Autonetics scientists agreed there was no reason they couldn't consider the computer, which had come of age by then, to become the main element in the silo's command and control system. This was a revolutionary approach, so revolutionary in fact that the group was uncertain about how the Air Force would react to the idea. But it was a simple plan. All that was needed would be to revise the ground software program and redesign the computer to increase its memory capacity and functional capability. Once again, the guidance and control system bore the brunt of the new challenge.
There was a point in early 1962. It happened to occur after a change in administration, and it was a few months prior to the fielding of the first operational unit of Minuteman I, when people in the administration and the Department of Defense suddenly realized that this juggernaut called Minuteman was coming down on them in a hurry, and they were a little bit uncertain as to whether or not the program could really proceed on the schedule it had and would give the results that they were after. And so the government commissioned a group of people to give an in-depth examination into the state of Minuteman I, how it compared with what the requirements were, and whether or not it was ready to go into the field in its envisioned operational status. The re-examination pointed out the need for some different characteristics in the evolving weapon system. And those characteristics included a lot more flexibility in a way the system could be commanded and controlled. It included some desired increase in accuracy, although not great. And it determined that the range of the system simply had to be increased for future use. And that was really the genesis of the Minuteman II development. We set about then to begin to answer the evolution and requirements that was taking place at this time. And so while Minuteman I was in production and being put into the field, we ended up launching into a Minuteman II development program to take into account these evolved requirements on the system.
The Minuteman II system was asked to meet a new accuracy requirement nearly 4 times better than that of Minuteman I, which was 67% more accurate than specified in the original requirement. To be compatible with the design of a new second-stage engine, the guidance system was required to incorporate a new method of control, liquid injection thrust vector control. Despite these increases in functional complexity, the guidance system was required to be much lighter and even more reliable than the as yet unproven Minuteman I.
We were really caught up tight on the changes that had to be made because the basic desire was not to upsize either the missile or the silo because of the expense of doing that, but rather to try and stuff these new characteristics and capabilities into the same size of missile that we had. The one concession that was made is that second stage was increased, but still stayed within the capability of the current silo and the basic dimensions of the missile. So we were faced with having to do a lot more than Minuteman I with less size and weight in the guidance system. There just isn't any other way you can do that to get additional range without cutting down the size of the payload. And a good part of the GNC system is in fact payload. It goes all the way to the end of boost. So we felt, among other things, that we just had to tap the state of art in microelectronics. And that turned out to be most feasible in the digital computer area and somewhat feasible in some of the control electronics areas.
This was a very ambitious undertaking. Microelectronic technology was so new that few electronic parts suppliers existed that could provide the components for this new design. To help develop the infrastructure needed for this advanced technology, Autonetics carefully chose those companies with the most potential and invested time, energy, and money to develop and incorporate this first large-scale application of microelectronics into a major weapons system. This developmental program proceeded during 1962 and 1963, concurrently with the early production and deployment of Minuteman I.
It was a risky thing to do because new technologies bring with it unsolved problems, and we had to get a reliability that was even greater than that desired in Minuteman I. So the decision was hard to come by, but we jointly with the Air Force decided to go ahead and micro-miniaturize the system to what we determined to be a practical extent at that time.
Because of the success of the guidance system's digital computer in Minuteman I, the Minuteman II digital computer was required to be expanded by a factor of 250% in order to take over the key message processing, secure coding, and monitoring and reporting functions previously performed by complex ground equipment in the silo.
It was clear that we probably could take some of that load off of the ground equipment by doing some more things in the missile computer. We had done a number of these things in the missile computer in Minuteman I, including self-check and the missile control and calibration and so forth. But now it began to appear that if we could just get the messages, communication messages, piped into the computer, that they could be processed there the same as you could process them in expensive ground equipment. And that the cost for putting it into the computer the incremental cost would be much less than the cost that it would take to generate new ground equipment. It was hard for some people to envision the missile computer lighting off its own first stage, and doing that in such a way that you met absolutely the requirements against inadvertent or unauthorized launch. And it was also difficult to think of putting all those top secret codes, if you will, into the missile computer. But all of those problems were overcome, and satisfactory solutions were worked out, and it turned out to be a tremendous asset to the program to do that. It was not really that difficult to sell, after we had resolved the basic sticking points on doing that. That was a fun period.
The Minuteman program led in application of yet another advanced technology, radiation hardening, when Autonetics scientists and engineers were required almost overnight to find ways for increasing missile survivability against nuclear attack. Late in 1963, the Department of Defense and U.S. Air Force identified and defined a new classified system requirement, the incorporation of a nuclear hardening capability, which in essence would make the system relatively immune to the hostile environments of nuclear weapon detonations.
The issue of surviving in a hostile nuclear environment became more and more important. And during the time Minuteman I was being fielded and Minuteman II was in early development, the people in Department of Defense and Department of Energy and some special corporations like RAND and Sandia Corporation finally began to get a good enough handle on how to characterize this threat that they could begin to quantify it. And this was studied at great length, finally to the point where it was presented to Department of Defense, and the decision was made to try and do something to make the Minuteman II system meet that requirement. And it was determined that it was an important enough thing that we should interrupt the program and respond to it.
Although this was a major high-risk change this late in the guidance and control program, the original deployment schedule of October 1965 was not altered. The detailed requirements for the classified changes continued to evolve throughout 1964 and were finally cast with a final major contract change in December of 1964.
In the early days of comparing the Minuteman system versus that requirement, it was clear that the design as it then existed would never make it through. It looked like a Swiss cheese, in fact, stacked up against that requirement. But the worst offender of all was the digital computer. And we, among a few people who had the initial look at the problem, it was decided that if we couldn't do something about the computer, it was worthless to try and do something about the rest of the system, where the problems were somewhat smaller but more amenable to change. The problem was that the digital circuits in the computer were extremely sensitive to this kind of transient radiation, and at the onset of the radiation, the computer could be counted on to bobble control bits and numerical quantities that it was processing, and to write gibberish into the memory. And that would have terminated any mission right at that point. The solution that seemed to be the most logical was to try and detect the onset of this pulse disturbance before it actually disturbed the computer circuits, and to put the computer to sleep, to disable its ability to write into its memory so that it could not alter anything that was already in memory. So we devised a method of putting the computer to sleep, as we referred to it, then having it wake up, pick up where it left off, make up for lost time, and continue on with a mission. And by that means, we were able to get around what was otherwise a tremendous problem in the misbehavior of all the computer circuits during that pulse of disturbance. With that solution pretty well laid down and proven by some experimentation, we were then able to address the rest of the system in terms of the control electronics and other portions of the computer, power supplies and things like that, and finally began to surround the redesigns that we would need to make the computer resistant to radiation of that specification. But we were able to do that, and with a few problems still remaining, the system was redesigned, and we got back on schedule and fielded the first unit on time in Minuteman. That was a successful program, and although it required a few modifications at a later time, the Minuteman II became the first system to be fielded that was designed to withstand the nuclear hostile environment.
Accordingly, Minuteman II missiles with increased nuclear survivability were rapidly deployed, and a whole new technology was born. The first all-up configuration of the operational missile containing the new and revised requirements was flown successfully in May 1965, only 6 months after the last major segment of the new requirements had been placed on contract and 5 months before the planned operational deployment. While the Minuteman II guidance system initially met or exceeded most of its requirement, it was not without problems. The very ambitious task of developing a new advanced microelectronic technology and incorporating it into the Minuteman II guidance system had been underestimated. The in-silo guidance and control mean time between failures, or MTBF, was shown by operational deployment to have been missed seriously. A higher MTBF number indicates better system performance and reliability. To give a comparison, consider that Minuteman I systems operating in the field since 1963 were achieving about 5,000 hours mean time between failures. In the early deployment stages of the Minuteman II program, guidance systems were achieving a mean time between failure rate in the hundreds of hours, rather than in the thousands of hours. This low in-silo MTBF contributed to an inability to logistically support the expanding Minuteman II fleet. The darkest days of the Minuteman program occurred during the one-year period from fall of 1966 to fall of 1967.
Some of you may recall that I think there were about 100 silos that were lacking missiles. That's how far behind we were in schedule because of this problem. And we negotiated a recovery program and appropriate dollars. I think the dollars at that time were without profit because Lee Atwood had negotiated with some of the generals that we would do it without profit. And we proceeded to not only meet that schedule, but beat it, so that in a rather short time we had all of the silos filled.
This highly successful recovery program led the weapon system out of trouble within a few months.
And then, as you may recall, the reliability numbers changed and started going up, and we did quite well. I always used to compare it, this is a humorous incident, I used to compare it to old wine, that the longer it aged, you know, the better it tasted. And I'll never forget some general saying to me, yes, it's like cheese, the longer it sits around, the worse it stinks. And I said, no, if you get past the smell, it tastes very good. But there was some interesting times.
Still, the ultimate story of the Minuteman II guidance and control program is one of unqualified success. The achievements in accuracy, weight, and in-flight reliability and improved operational reliability increased Minuteman II system effectiveness by 20% over requirements. A total of 805 Minuteman II guidance systems were produced by Autonetics, and after having overcome the design problems, Minuteman II had successfully utilized integrated circuits and leapfrogged into a completely new state-of-the-art technology called microelectronics.
At one time, probably in about 1964, we had more than half of all the integrated circuits being built in the world, to our knowledge, at least in the free world, coming into the Minuteman program.
I think it's well known that the development of the reliable electronics parts probably pushed the state of that art throughout the country by several years.
If it were not for the Minuteman program, there wouldn't be a Silicon Valley today.
By the time the Air Force had identified new strategic requirements beyond those of Minuteman II, the Autonetics technical team had already been at work designing a greatly improved and upgraded guidance and control package. During the 1964-1965 timeframe, a joint internal venture between North American Aviation's Autonetics and Rocketdyne divisions had developed the concept for a new post-boost control system. This system would provide a greatly improved method to precisely control the velocity and attitude of the reentry vehicle at the point of release from the missile. With this technology breakthrough came the next generation of Minuteman with a significantly increased mission capability. Major features of the new missile, which would become Minuteman III, were its new third stage, the post-boost propulsion system, and its multiple independently targetable reentry vehicle, or MIRV, system. With MIRVs, each Minuteman missile now could carry up to 3 warheads, each aimed at a separate target. But as in other new development efforts, this challenge again had placed Autonetics scientists in new territory.
The challenges presented by Minuteman III to the Autonetics team were many and varied, but there were 2 that stand out in my mind as somewhat unique. The post-boost propulsion subsystem and the deployment of multiple independently targeted reentry vehicles come to mind. And they were severe challenges, not only because they were formidable technical problems in themselves, but because they were problems that we were not uniquely qualified to deal with. The propulsion subsystem certainly wasn't our bag, nor the deployment of space vehicles was something we had not encountered before. So those 2 stand out in my mind as the real challenges that we had. And I recall that when we first started working with the Air Force to show that the MIRV concept was feasible, it could be made to work, that the state of the art was here in terms of technology, we worked with our own Rocketdyne division on the propulsion aspects. So then when the Minuteman III concept was approved, and we were told to move out in April of 1966, we went through a competition to select the supplier of the propulsion subsystem. We started out with Bell as our supplier, and the first thing we found out is we had seriously underestimated the cost of the research and development program. Badly underestimated it. And it continued to grow and grow and grow and grow until it became of great concern to the Air Force. But on the other hand, they were deeply committed to the program, and we pressed on, and finally produced the first of the R&D flight test articles, the missiles, the propulsion subsystem, the guidance, and so forth. And all of the problems that we were deeply concerned about seemed to work out very well. The ability to fabricate a totally sealed propulsion system, to control small rocket engines, to maneuver in space. Everything worked just about the way it was supposed to work on paper. And we got bit by an unknown unknown. I recall I went on vacation in the fall of 1969, and when I came back from vacation, we had had a flight failure. Subsequent to that, we had another flight failure, and then a third flight failure. And these failures all had somewhat similar characteristics in that they appeared as if there was an intermittent failure of some sort in the electronics. That was the first thing that people saw that made them wonder what was the nature of what was happening to us. And a good deal of expertise, both from Autonetics, from TRW, from the Air Force, from other companies, was applied to the problem, and it was decided that it must be loose particles inside the integrated circuits were what was causing the problem. That is, small pieces of gold floating around inside and intermittently shorting out parts of the integrated circuits. And if that was the case, then we had a serious problem on our hands, because we had already paid for $50 million worth of electronic parts, and they were sitting in our warehouse at the time. And if they were suspect, that is, if they were not flight worthy, it posed a problem to the program that was almost insoluble. So a good many people thought about it and thought about it and thought about it and decided, and I would have to give credit to Bob Knox as the main architect of this thought, that perhaps we could run the parts through a vibration test to cause the loose particles to evidence themselves early in the game and could be eliminated, so that by the time we passed the vibration test, the equipment would indeed be flight worthy. And so we undertook to do that, and that became known as the Alligator program. There have been many theories propounded as to who dreamed up the name Alligator and what significance it had, but I don't know who originated the name, but I do believe it came from the old saying, when you're up to your alligators, it's sometimes difficult to remember that your original intention was to drain the swamp. And that's about the condition we were in. We had so many things to do. We had a schedule that the Air Force refused to give us relief on, and yet we had to introduce a whole separate screening process into the production units. And it turned out that there were bonuses to the company and the Air Force, that the screening process apparently not only solved the in-flight particle problem, but it improved the reliability of the equipment to the point that it turned out to be outstanding. As a matter of fact, we had a reliability incentive clause with the Air Force, and we exceeded the goal by a factor of about 3 on the mean time between failure, and a lot of people think that was due to the Alligator screen.
In 1966, the first engineering model computer for the Minuteman III missile was completed 2 months ahead of schedule. The microelectronic computer, the D-37D, had twice the memory capacity plus other improvements over Minuteman II equipment. A new self-alignment technique developed by Autonetics provided automatic primary self-contained azimuth alignment, which eliminated a very long and complex alignment process of an external reference performed by Air Force teams. To give you an example of the complexity of this task, aligning a Minuteman missile to accomplish its intended mission might be compared to threading a needle 400 feet away or kicking a field goal at 300 miles. The Minuteman III further increased the system's survivability, again vastly expanded the digital computer heart of the missile, increased flight capability, added an innovative liquid injection thrust vector control, and unveiled a new post-propulsion system for the ultra-refined targeting. On August 16, 1968, the first Minuteman III research and development missile was launched from Cape Kennedy. The first unit of operational Minuteman III missiles were on station at the Strategic Air Command's Minot Air Force Base in North Dakota in July 1970. By this time, the Minuteman I missile was being phased out and being replaced by Minuteman IIs or Minuteman IIIs. In 1972, the United States began a program of ICBM modernization in response to the anticipated threat posed by a new generation of Soviet ICBM forces. The idea for a next-generation guidance system was brought to fruition in 1973 under an Air Force concept definition contract known as the Advanced Inertial Reference Sphere Missile Performance Measurement System, or MPMS program. After winning the contract, Autonetics began work on what became known as the Minuteman III MPMS program. The objective of this program was to demonstrate advanced ballistic guidance technology by flying an advanced inertial measurement unit piggyback on the Minuteman missile. Autonetics would build and fly a wafer using the Advanced Inertial Reference Sphere Inertial Measurement Unit, or AIRS-IMU, supplied by Charles Stark Draper Laboratory. This technology later was used on the MX, or Peacekeeper missile.
We had started out with the idea of making the Minuteman III a self-aligning system for the first time. We had a gyro compass on the Minuteman II system, but it was only used to extrapolate an optical reference that was provided in the silo. Then subsequently we developed a scheme that allowed the Minuteman II gyro compass to provide a self-aligning capability, and that was then backfitted into the Minuteman II systems. In and around this same time, about 1973, the Draper Lab had been working on a new so-called floated ball IMU called the AIRS, A-I-R-S, Advanced Inertial Reference Sphere. And it had progressed quite a long way and used the instruments which were called third generation inertial instruments. These are Draper Labs. This is the lab that's in and around MIT, Charles Stark Draper Lab. And they were using the so-called third generation inertial instruments. And it had progressed to the point that they felt that this was work that they were doing for BMO, for the Air Force. And they felt that they were on the verge of being ready to flight test this concept to show that it was feasible. And they were looking for super high accuracy. And it's sort of a unique concept in that all the systems that we had always had, the tricky part about aligning, pre-launch alignment of a system is in the azimuth orientation. Leveling is fairly simple, but the azimuth alignment's rather difficult in general, and this floated ball created a rather significant problem in that you couldn't tell what the alignment accuracy was until you fly or do something to provide a disturbance like some acceleration, say a sled test. So the Air Force at that time decided that they would have a flight test of just Minuteman III with another wafer, which would be called the Missile Performance Measurement System, and it would include this AIRS-IMU. And there was competition, I think about '73, and we won that competition to integrate this new Draper Lab sort of advanced development IMU into this missile flight. And that flight eventually occurred about the bicentennial time. It's very, I know it was very close to that time because there was a picture on the wafer or something or other of the Minuteman or some such. I recall that much. At any rate, that was beginning of sort of experimental uses of the Minuteman III missile. It turned out there were a few problems with that, but we learned quite a bit, and eventually that IMU was the one that was selected to provide the navigation capability for the MX, or Peacekeeper missile.
Well, in the early 70s, the Air Force had come up with the desire for a hard target kill missile. And what they had come upon was a very large missile, about 8 stories high, 8 feet in diameter, weighed a couple of 100,000 pounds. It had to have the hardness that was 3 times better than Minuteman and accuracy that was 3 times better than Minuteman. and they wanted to deliver 10 re-entry vehicles at the same time. It was a very, very powerful weapon that was meant to eliminate hard targets in the Soviet Union.
In September 1979, Autonetics began full-scale development of the MX, or Peacekeeper, Missile Guidance and Control System. Autonetics developed and manufactured the Missile Electronics and Computer Assembly, or MECA, which contains most of the guidance and control electronics, including the missile's onboard computer. The division also provided operational ground and flight software, which it integrates into the missile guidance and control set, along with the Air's Inertial Measurement Unit built by Northrop under a separate Air Force contract.
There was nothing that was really technologically advanced from Minuteman onto Peacekeeper, but we did, however, have a different concept. The concept here was that the whole MGCS would be a drawer that would fit into the side of Stage 4 and would be easily removable for maintenance reasons. You wouldn't have to pull Stage 4 out of the hole in order to repair the system. This was really important. We decided that on the computer portion of that, we were going to combine the computer and the flight control into one large box that was called the MECA, the Missile Electronics and Computer Assembly. It was the biggest thing we had ever built in the way of a hermetic box. Around 3 cubic feet, 180 pounds, had 15,000 electronic components in it, really big box. And of course, went into the MGCS, which was about 425 pounds. The drawer itself was very large. We had a little bit of trouble at the beginning in that we didn't think we were pulling engineering together well enough. We asked for a chief engineer, and the chief engineer turned out to be Tom Gunkel, who's probably about the best guy you ever could have selected for a job like that. And with Tom running things in engineering, the program really took off, and we did very, very well.
Specifically looking at the radiation-hard CMOS sauce, we got a development contract from the government. We called our project ABC, the Advanced Ballistic Computer, but actually that was the short name. The full name was Advanced Ballistic Computer, developed especially for guidance systems, went on through the whole alphabet. And to pronounce that, that was Project App Gedefke Jekvil Nakvin Stuvitzes. But most people couldn't handle that, so we called it ABC. And what we pursued was very advanced packaging. In fact, some of the packaging ideas that we had then are just now coming into use. Pursued it with the government and our own IR&D. Ended up not using all the technology. The CMOS sauce we didn't use until a small missile. Some of the circumvention approaches we did use on Peacekeeper. But what it did was it made us the advanced computer supplier in the eyes of the customer. So when we wrote our proposal, and it was a competitive procurement, we knew we were playing into the right audience in terms of technology. With that computer development, we won the flight computer. The guidance integration job was actually competed separately, 2 different jobs, whereas in the past it had just been one job. We also won the guidance integration, which also was a competition. And then after we were awarded the 2 contracts, they were combined into a single contract, which was the Peacekeeper Development Program. Software was an area I think we surprised people. Did very well, but only because we worked at it. We had Monday afternoon meetings each week to go over all the software issues and problems, just to keep a focus on it, and it seemed to work. Parts, always a problem, but there too we made it. At the beginning of the program, we started off overrunning, and when I became chief engineer, we were still increasing the size of the overrun, and that peaked around $12 or $13 million. But by focusing on it, we turned it around and then ultimately underran the contract by $50 million across the 2 development programs.
I think some of the things that were challenging on the program, one of them was the massive amount of material, including subcontracts. 65% of the program was either subcontracted or supplier money. It was by far and away the biggest thing I think we've ever done in subcontracted or material effort, and that was a significant challenge because the subcontracts were important. Both memories were there, staging connectors, the umbilical group, in-flight coolant assembly, batteries. So there was a pretty good effort that was required to manage all that, and we didn't have near the trouble that we had seemed to have on other subcontracted efforts on other programs. We also on Peacekeeper went to the first automated manufacturing cell and automated material system. This was done in conjunction with the Air Force on their Tech Mod program. Between the two of us, I think we invested around $17 million in this Tech Mod factory over in Building 270. The automated material system worked out fabulously. I mean, nobody has ever looked back to see how much money was saved by that, but it had to be astronomical across the campus because it just eliminated warehouse problems, essentially. There were some other new things. We instituted just-in-time manufacturing, if you will, to eliminate problems of too much inventory, too many assets lying around, losing of parts because people would go into kits and pull them out. It was a gamble, something that I myself was not quite comfortable with. Having come from the parts area, I wanted those parts where I could get my hands on them, but the customer went along with it, our manufacturing people went along with it, upper management went along with it, and it worked out very, very well. We also instituted other things out on the floor as the TQM activity came in place. We put a integrated product team of engineering, multifunctional people into the factory. About 3 or 4 years ago, that has worked out fabulously well. But more than that, the dedication of the entire team to this program, I don't know how it was on Minuteman. I worked early Minuteman, but I did not work Minuteman 2 or Minuteman 3 until much later stages. But the dedication of the 1,600 people on Peacekeeper was something for a person to really behold. If there's any one thing that I think was the mark of success, that was it. The teamwork on the program, subs, suppliers, TRW, Northrop, just everybody, the customer. It was incredible. We didn't have any controversy to speak of. Oh, yeah, you'd worry about little things day to day. But from an overall standpoint, never did we have controversy that interfered with the program. Subsequently, consequently, we made just about every schedule that a person could possibly dream of making.
On April 6, 1983, after nearly a decade of debate over the precise basing scheme for the Peacekeeper, President Reagan announced a plan to base 100 Peacekeeper ICBMs in modified Minuteman III silos at Francis E. Warren Air Force Base in Wyoming. However, in August 1985, Congress capped the number of Peacekeepers in silos at 50. Also in that same year, the Peacekeeper ICBM successfully flew its first test flight. The missile recorded a string of 18 consecutive successful R&D test flights and was hailed as the most successful development program of its type in U.S. Air Force history.
First flight was successful. And I wasn't there, but I remember the excited phone calls I got from the people that were there. There was an overcast, and so the missile went up into the overcast and you couldn't really see, and everybody had to stand around and wait for the telemetry to come in to find out if it had been a success. And of course it was a success.
For us, the first flight was terrific. The flight program itself, we were 18 for 18 in R&D flights, 10 for 11 so far in operational test flights. We had 3,000 items of AVE hardware to deliver. 99% of those were delivered on or ahead of schedule. We underran every contract. The performance of the hardware has been absolutely fantastic, nothing short of fantastic.
The Peacekeeper program achieved a perfect flight test record and reached initial operational capability on December 22, 1986, when the first 10 Peacekeeper ICBMs became operational. This was 11 days prior to the program IOC date scheduled nearly a decade before. The entire complement of 50 peacekeepers reached full operational capability on December 16, 1988.
At the present time, the Mecca itself is running at an MTBF about 100,000 hours, and the MGCS without the IMU in it is running at about 80,000 hours for MTBF. The parts that we developed way back on the AGS program have operated now for 10 billion part operational hours without a single failure. The subcontracted hardware is performing tremendously. So the program was just a fantastic success. It doesn't matter which way you look at it.
In 1983, a bipartisan commission on strategic forces chaired by Brent Scowcroft evaluated America's ICBM modernization requirements. To achieve those objectives, the commission concluded the U.S. should do the following: deploy 100 MX missiles in existing Minuteman silos to satisfy the immediate needs of the U.S. ICBM force with a study of a follow-on basing mode to increase survivability. Carry out research and development of a new single warhead ICBM to be transported on road launchers specifically designed to withstand the effects of nuclear detonation, and seek arms control agreements designed to enhance strategic stability. In 1984, Rockwell was awarded a pre-production Air Force contract for integration of a guidance and control system for the next generation ICBM called the Small ICBM, a single warhead missile proposed as a highly survivable mobile weapon system. The goal of the Small ICBM program was to incorporate advanced technology to enhance the reliability and maintainability of the missile.
After Peacekeeper came Small Missile. We again had to compete. Wrote, I think, a very good proposal and won. Started down the path of a major development program only to have the country falter in its desires, and so we had that program terminated. Went on a few more years with Small Missile. Interest again turned around, and we got another very large development contract, in both cases about $500 million. And then shortly after we won that, they terminated it a second time. So I think while we performed very well on Small Missile, it's been a frustrating experience of getting everything up to steam and moving ahead with momentum, and then having the government terminate it. Another thing that happened in the same time frame was us becoming the second source for the AIRS IMU. Started off with our qualification program, where again it was a competition. We put together what we thought was the lowest cost proposal. Actually had the pricing people tell us how we could make it lower priced. First time that's ever happened to me in writing proposals, since their job is to try and be conservative. Second contract was a shared bid with Northrop. We won 9 units, which was a small portion. The next bid was for a winner-take-all, and we beat Northrop and went on contract to go into production. And for a few months there, we're the sole remaining production supplier of AIRS IMUs.
In keeping with the original modernization goal of deploying a survivable mobile ICBM, the Reagan administration directed the creation of a rail-mobile peacekeeper force. The rail garrison program called for redeploying 50 silo-based missiles to rail garrisons at existing Air Force bases. The trains would be maintained on strategic alert in secure areas on existing Air Force bases for day-to-day operations. The trains would leave their garrisons only in time of national need and be deployed onto the U.S. rail network. 50 peacekeepers would be deployed aboard 25 specially built trains, with each train having 2 locomotives, 2 missile launch cars, a launch control car, a maintenance car, a fuel car, and 2 security cars. Rockwell's Autonetics Strategic Systems Division played a key role in the rail garrison program. In May 1988, the division was awarded a 5-year, $162 million contract to design, develop, and test the U.S. Air Force Peacekeeper Rail Garrison Launch Control System, which included the launch control car and the 2 security cars. However, while U.S. ICBM modernization continued, developments around the world would soon impact the work being done not only at Autonetics, but also at facilities of defense contractors throughout the country.
I personally think, and the people on the program think, we actually made a contribution to the nation's safety, the nation's defense, and our contribution to bringing down the Berlin Wall and the change in Russia as they attempted to compete with the technology and engineering that we were able to put into our systems.
In the late 1980s, the Soviet economy had reached the breaking point and simply could not withstand the price tag of their arms buildup, along with the burden of maintaining their worldwide empire. The result was a bankrupt Soviet economy and the dissolution of the Communist Party. START I, the superpower agreement, was signed in July 1991 by President George Bush and then Soviet leader Mikhail Gorbachev in Moscow. On January 3, 1993, President George Bush and new Russian leader Boris Yeltsin signed the second Strategic Arms Reduction Talks Treaty, START II, locking in cuts so deep that neither of the former Cold War foes could have an arsenal large enough to wage a surprise nuclear attack on the other. The long-standing threat of communism was gone, and the new age of peace was at hand. And everyone in the defense industry joined the world in celebrating this new era and took pride in their contributions toward this new peace. A bittersweet victory note rang out, however, when Congress re-evaluated the need for America's ICBM modernization programs. In its September 27, 1991 speech that would impact every defense and aerospace worker throughout America in some way, the Bush administration canceled several major defense programs. In response to the announcement and congressional approval, the U.S. Air Force announced on October 11, 1991, the termination of a contract with Rockwell's Autonetics Division for the Peacekeeper Rail Garrison Launch Control System. In January 1992, the small ICBM contract was also canceled. But the true heritage of the ICBM fleet, the strategy of deterrence which had been spawned 40 years earlier, had been successful. Former President Ronald Reagan said it best when he reviewed the series of arms control agreements the U.S. and Soviet Union have signed over the years. In essence, he said they would have been impossible without the defense buildup. Specifically, he said, modern history suggested strongly that the men in the Kremlin respected strength and exploited weakness. A large part of the strength the Soviets respected was the Minuteman and Peacekeeper ICBM force. But the chapter in the history book of ICBMs is not yet closed. To help compensate for the dramatic reductions in the nation's ICBM force, the Department of Defense has designated the Minuteman III as the backbone of the U.S. ICBM fleet and announced plans for a Minuteman III guidance replacement program. The program objective is to extend the life of Minuteman III beyond the year 2020 by providing highly maintainable, cost-effective replacement electronics for the aging NS-20 guidance set. In this role, Rockwell will continue to provide the technology and support which will strengthen our nation's security well into the next century.
Hello again, and welcome back to the 1990s. As you've seen, the background of Rockwell's North American aviation and Autonetics organizations can best be described as a history of achievement. These achievements have contributed to the changes and technology advances that have brought America full circle, from the reality of the Cold War to the present era of superpower peace. Our work on all three generations of Minuteman and the Peacekeeper program set the pace for the research, development, and production of the most accurate inertial guidance and control systems in the free world. No higher tribute can be paid to the men and women of Rockwell than the knowledge that their fellow Americans can always depend on the unprecedented reliability of the Minuteman ICBM fleet, which continues to be the backbone of the nation's defense. These men and women are still very much proud of the past and poised for the future.